Good morning, everyone. This is Physics 46, and today is, what is today? September the 15th. This is a continued lecture on chapter 21, and we will be going off of the last problem. This is it's an important day to be at lecture. We're really going to get into really the heart of how you attack objects that have an electric field. We're gonna pick some simple objects, but they are mathematically can be quite sophisticated, and you will see in a little while. So before we get started, does anybody have any questions? All right. I will say, if you have lab today, please bring your first day handout that has the first lab in it. That lab you can do pretty quickly. That lab is probably about an hour and a half, but what I'm going to do is let everyone finish their labs today, and then we're actually going to start to learn how to use a ammeter, or what you call a voltmeter. We're going to just get practical. I'm going to teach you how to go to your car and measure the voltage on your battery. I'm going to just teach you some very basic stuff about how to approach those types of situations, so you know what to do in order to even see if your battery in your car is holding the proper charge. The details behind all that you'll learn later, like how a battery actually works, how charge is stored, and how charge moves on conductors. But that being said, we need to understand all these details here now. So our last question, what is the E field at a point between two charges? So we had a negative charge here to the left and a positive charge to the right. We have the distance relative to negative charge. We'll call that R1 is equal to 2 centimeters and R2 is 8 centimeters. So we know the total distance between the charges is 10 centimeters. And I'm asking you, what is the E field at that point? And that's just a point I picked. It could be a point anywhere along that whole distance between the negative and positive. Now, why does E1 point to the left? Let's see if anybody remembers.
Is the E field going in?
Yeah, for negative charges, the E field goes in. For positive charges, the E field goes out. So if the E field is going in for the negative, it's going to point to the left. And for the positive, the E field's going out. So E2 is also going to point to the left. If we have our regular number line to the left, it would be negative. So if you add E1 plus E2, and we've defined the electric field for point charges to be KQ over R squared. So you would just add those two, the sum, the net E field at that point. We got negative 6.3 times 10 to the 8 newtons per coulomb. That's the strength of the electric field at that point. So how is that useful to us? Well, let's say that is part A. Let's do part B. And essentially, Part B is creating what you would call an electron gun. If an electron, the mass of the electron, does anybody know the mass of an electron?
Really, really small.
I think I know, 1.37 times negative 27 or something like that.
No.
That was close. I have it in my homework, I swear.
1.6 times 10 to the negative 19.
Wow, oh, never mind.
Oh, that's the charge.
That's the charge,
Oh, okay.
the mass of an electron. So if an electron is placed at rest at point P and then released, what will be its initial acceleration? Magnitude plus direction. So here's my negative charge, here's my positive charge, and there was my point P. And I'm going to put an electron right there. So if I place an electron right there, first of all, what direction is the electron going to take off in?
The right.
To the right.
It's going to move to the right. Why is it going to move to the right?
Because it's going to be repelled by the left particle and attracted by the right particle.
Correct. So we know that it's going to take off with an acceleration to the right because of those electrical properties. Negative and negative repel, negative and positive attract. But we want to know, we want to know the acceleration.
Padilla?
Yeah.
If the acceleration is to the right because it's attracted to the positive charge and it's repelled by the negative charge, would that mean that force vectors and acceleration vectors have the same direction? Or does it not correlate at all?
No, that's why we're actually we're doing this type of problem. We got the total electric field.
Uh-huh.
We just calculated that in part A, right?
Okay.
And remember that electric field is associated with the electric force. Electric field is equal to the force electric over the charge that we're going to put at that point.
Mm-hmm.
So that charge right there is the charge of what?
Of the electron.
Of the electron. So we already have we already know Q, we have everything we need. So all we need to do is solve for the actual acceleration here. But how does that fit into this equation? So I could say force electric is equal to Q of the electron times the electric field. And the electric field, the sum that we got was the number above. Negative 6.3 times 10 to the what? 8th newtons per coulomb.
Padilla?
Yeah.
The electric force is like, it's not like other forces, right? Where you can say like the sum of the electric forces equals mass times acceleration and da 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 da, right?
Well, you could get the sum of the forces by doing what we had previously done with other problems. The force,
yeah, but you can't equate them to mass times acceleration like you can with other forces, though, right?
Can't. Why not?
Oh, okay. Let's do that then.
Let's do that then. Well, we know force electric is Q times E, right? But that force electric is also putting a force on it such that that mass, which would be the mass of the electron, is going to have an acceleration. So to answer your question, yes, you can. Remember, force equals mass times acceleration is a general overview, Newton's second law, of anything that has mass. So you can say the force electric is equivalent to a mass times acceleration, except what is that mass? That's the mass of the electron because of that electric force. So in this case, you could say force electric is also equivalent to force is equal to mass times acceleration. Because I'm telling you, it's going to move and it starts from rest. So what can we do here? Just simply solve for acceleration. So that charge we know is what? What's the charge of an electron? 1.60. We'll just put 1.60 times 10 to the negative 19 coulombs times that electric field, which is 6.3 times 10 to the 8th newtons per coulomb, all divided by the mass of the electron. So take out your calculators and give me a number here. 9.11 times 10 to the negative 31st kilograms. Coulombs cancel.
1.1 times 10 to the 20th.
Anyone else get that?
Yeah.
Yeah.
1.1 times 10 to the 20th meters per second squared.
That's fast.
That's fast.
Where does the seconds come from? From the newtons?
So the coulombs cancel, you get newtons per kilogram, right? What is Newton? That's a force. That's mass times acceleration. That's kilograms times meters per second squared divided by kilograms. Kilograms cancel and you get meters per second squared.
Thank you.
That's just a quick unit analysis using your units. Okay. Any questions on this?
Yeah, can we use that formula every time to find the acceleration?
Absolutely.
All right, cool.
But what do you need?
Oh, you just need the mass of the electron, the key.
That's right.
Okay, gotcha.
So if I asked you right now, oh yeah, and direction would be positive, right? So I'd put positive there.
All
or
right.
you can write to the right. So I use the vectors to tell me. I'm not plugging in the negatives right now. There will come a point where those negatives, we will need to plug those in, but that's not until chapter 23. So for right now, you're using, that's why you have to draw pictures. And from 44, what was the first thing? Every single problem, what's the first thing you do?
The body diagram.
Draw a picture. Draw a picture. All right. And it's especially true for these types of problems. To know that negative goes in, positive goes out. That's our rubric. That's how we're understanding our problems. That's how we're attacking them. Could we have chosen it the other way in the very beginning? All the other mathematicians, all the other, yeah, of course. But this is the way we chose to figure it out. All right. What if I put a proton right between the two? That has the same exact charge, right? Which way would the proton accelerate?
To the left.
To the left. because it's positively charged. Would the proton's acceleration be as great as the electron's acceleration?
No,
It would not. Why not?
it has a bigger mass.
Because the mass of the proton would be greater. So that would be a smaller acceleration. But indeed, you can accelerate a proton. This would be a very simple way to accelerate a proton. And accelerating protons is, part of what I did at the lab. There's also a proton accelerator over at Loma Linda to actually treat cancer. They ram protons into cancer cells to break up the cancer cells. We will be talking about stuff like that later on in this class. We'll also be talking about some interesting stuff like MRIs or CAT scans. How do those work with electric and magnetic fields? We'll be going over some pretty cool stuff. All right. Next problem, calculate the total E field magnitude plus direction A at point A, B at point B, due to charge Q1 and Q2. All right, here's the setup.
Is the second part of the question due to charge 1 and charge 2? Is that for both A and B or just B?
For A and B.
Okay.
Can you scroll a little bit down, Professor, please?
There you go. Oh no.
What the?
Let's do point A. The length right there, and I'm going to give you that length. That's 60 centimeters. And just to make things easy, this is 30 centimeters. And if we were to do the trig on that, that's going to be 30 degrees. That's positive charge. That's a negative charge. So now we're going two-dimensional with the electric field. Very, very similar to the force problem. So what is the total electric field at point A due to Q1 and Q2? So we can just simply write out the vectors right now. Which way will the electric field point due to Q2 at point A? Gabby.
Oh, yeah. In towards the Q2.
Okay, is the Q2 positive or negative?
It's positive.
So does the electric field propagate out of a positive or into a positive?
I put that it goes in. Did I write it wrong? Does it
Yeah,
go-
positive is always out.
Okay.
So which way would the electric field point at point A due to Q2 on the axis?
It would point out.
Up.
Or out, up.
Up.
Wait, why is it up and not all over? Oh, I see. Yeah.
Because we're using our axis. All right. Now at point A, which way is it going to point due to Q1?
It's Q1.
Exactly in a straight line towards Q1. And actually it's going to be, should be shorter. Why would it be shorter? Why would the magnitude of the vector be shorter towards Q1 as opposed to Q2?
It's farther away.
Distance is further.
That's further away. And we know that the electric field associated for point charge is KQ over R squared. So it's a function of distance.
It would be exactly half, right?
We can
Like-
calculate that.
Order.
Calculate that.
If it was just double distance.
Oh yeah, you're right.
And
Yeah,
we're actually
no,
going to
'cause the
calculate it
triangle.
right now. Well, it's an R squared dependent.
Yeah.
So I'm going to label these. The electric field at A due to charge 2, the electric field at A due to charge 1. So if we just drew a parallelogram real fast, we know that E net would go that way. Again, chapter 3, Giancoli, tip to tail method or parallelogram method. So very similar how we did forces, force electric. We would sum up the forces due to Q1 and Q2 in the X and Y dimensions. That's it. So let's go ahead and attack that. Let me go change the color. So A, at point A, the X dimension, the Y dimension. So E, let's do this, E2, A2X. What's the electric field at point A due to charge 2 in the X direction?
0.
0. EA1X is equal to what? Well, if we look at EA1, oh, it breaks up into vectors. EA1X, EA1Y. And what's this angle right here?
30
Isn't it
degrees.
30?
30 degrees. So EA1X would be EA1 cosine 30 degrees, and EA1Y would be EA1 sine 30 degrees. So EA1X would be EA1 cosine 30 degrees. Then you would sum up the electric field in the X direction, which would be EA2X plus EA1X. Is this making sense to everyone?
Mhm.
All right. Y dimension. EA2Y. What's EA2Y?
Just EA2.
Just EA2. EA1Y. Well, we just wrote it. EA1 sine 30 degrees. Then we would sum up all our Y components. EA2y plus EA1y. What do we
EA1Y,
need?
right?
Say that again, AJ?
Would it be minus EA1Y?
Yeah, but we're gonna
gotcha.
embed that into, and we'll do it right now. Negative. Is that important?
Mm.
Yeah, that's important because that vector is pointing downward. So we need the magnitudes. We need the magnitudes of EA1 and EA2. So let's go ahead and calculate those. EA1 would be K Q1 over R squared. And let's do that. 8.99 times 10 to the 9 newtons meters squared over coulombs squared times 50 times 10 to the negative 6 coulombs over, what is it? Q1 is 60 centimeters, so that would be 0.60 meters squared. EA1, I got 1.25 times 10 to the 6 newtons per coulomb. Somebody double check that.
Yes.
Yeah.
Same thing.
Okay. EA2 would be same thing, except the distance is 0.30 meters squared. And EA2, plug that in your calculator, and I get, so that's going to be larger, right? 5.0 times 10 to the 6 newtons per coulomb. Anybody else get that?
Same thing.
All right, good. So we have the magnitude. So now we can move on to getting the net electric field at point A. Why is that important?
I mean, that was the question, so that helps. But it allows us to drop in any charged particle there and see how it moves initially.
Exactly. We could drop any type of charged particle there and we would know the direction of movement, just like we did in part B. We dropped an electron between those two charges, right? So finding the net electric field at a certain point allows us to give direction to any type of electric particle gun we want to produce. If you're so inclined.
When you ask for the direction, are you simply asking for like, is it moving positively or negatively? Or are you asking for like what we did, not yesterday, sorry, on Friday, where you did like the theta and then inverse tangent, like you will get a degree. Is that what that means? Or no?
It just means based off of the positive and negative, it's going to give a direction, a net direction. And depending on the type of particle you put at that point, it's going to go either that way or 180 degrees the opposite way.
Oh, okay. So, okay, that makes sense. Okay, I see.
Right?
Yeah.
Because if it's a positive, if I put a positive particle at point A, is it going to follow E net or go directly opposite of E net?
The opposite? No.
It's going to follow E net.
It's going to follow E net, right? Because if I put a positive particle there, what does that positive particle want to do with Q2?
Go away from it.
Push it away, right? But at the same time, that positive particle at point A is being pulled by what?
Oh,
Q1.
Q1, so it shoots off to the right there into the first quadrant. Does that make sense?
Yeah, that makes sense. Thank you.
Now, if I put a negative particle there, what happens?
It would go the opposite of E net.
It would go the opposite of E net. Very similar to our argument if we put a proton here. If we put a proton here, we know it would shoot that way. All right. Everyone following me so far? Good to go?
Mhm.
All right, let's sum up our E fields. So the sum of EX would be E2X, EA2X is 0, EA1, and EA1 is 1.25 times 10 to the 6 Newton per Coulomb times cosine of 30 degrees. Somebody give me a number for that. And then somebody give me a number for Y. EA2. EA2 is just EA2, right? 5.0 times 10 to the 6 Newton per Coulomb plus EA1, which would be 1.25 times 10 negative. Don't forget that negative.
The sum of the E's and the X, it's going to be a 1.1 times 10 to the 6th, or 1.08 times 10 to the 6th.
1.1 times 10 to the 6 Newton per Coulomb. If anybody disagrees, please let me know. And then 1.25 times sine 30 degrees, the sum of the y's. What's the sum of the y's?
Oh, that's just 3.75 times 10 to the 6th. Oh, no, I'm stupid. Ignore me.
I got 1.25 times 10 to the 6th.
5.0 sine 30 degrees. What's sine 30 degrees? That's 1/2, right?
Yeah.
So like 4 point, no, I can't do math. Never mind.
0 times 10 to the 6th minus 1.25 times 10 to the 6th divided by 2.
4.4 times 10 to the 6.
4.4.
4.4.
Yeah.
It's annoying how like simple it would seem dividing 1.25 by 2 is, when in reality you're like, ah, crap.
0.625. Okay. I think the consensus is 4.4. That's what I got.
Yep.
Yeah. Okay. So very similar. What do?
Find the magnitude.
Find the magnitude. We know E net is pointing that way. That's the sum, e to the x. That's the sum, e to the y. And we know we got a positive number there and a positive number there, so we can write that. Oops. This can be a theta. So, E net. Square root of the sum of e to the x squared plus e to the y squared. Putting that in. We get 1.1 times 10 to the 6 Newton per Coulomb squared plus 4.4 times 10 to the 6 Newton per Coulomb squared.
4.54 times 10 to the 6th.
E net. 4.5 times 10 to the 6 Newton per Coulomb. And the direction.
Let's find out.
So we'll say tan theta is equal to what?
EY over EX.
EY over EX. Theta is equal to inverse tangent. EY is basically 4.4 over 1.1, right? Times 10 to the 6 in Newton per Coulomb all cancel.
76 degrees.
Theta is equal to 76 degrees. So that angle relative is 76, relative to the x-axis. That were the x-axis right there. All right. So that's the sum and the sum of the E field magnitude. E net is 4.5 times 10 to the 6 Newton per Coulomb, and the angle will shoot off is 76 degrees relative to the positive x-axis. Gabby.
If it was, like you said, if it was like if it was the opposite of what it is now, that means we would add 180 degrees
Yes.
to the angle. Okay.
Yeah. It all depends on the charge you put at that location.
Okay.
Gotta love vectors.
Indeed. Okay. Let's go back up here and analyze point B.
Oh crap, we're not done?
No, we just did part A.
Yeah, Padilla, promise me you're never gonna put a problem like number 13 from the Giancoli on a freaking test.
Dude, that was
Because
so
holy crap, dude. Took me 2
Oh.
entire pages of paper to do.
Oh, good job.
Ouch.
2 pages? What are you doing
Yeah,
to these
I
trees,
definitely
man?
didn't write that much for sure.
One-sided.
Some of us
That's
are
compact your writing.
math in our head.
Yeah, that's 2 pages is a lot.
Remind me what
Okay,
13 was again?
It was where they gave you 3 particles in a equilateral triangle, and they wanted
Oh
you to-
yeah, that's a fun one.
yeah.
You're supposed to use symmetry arguments, man.
With what? They don't have equal charges.
Oh,
Yeah, no, they all, yes.
No, that was
they
the
did.
that was the one after that. 13 is the triangle one, the one on the
Yeah,
square.
but like you can use symmetry because like the forces between each particle is like the same. You don't have to do it for each individual part. I don't know. I did symmetry somehow.
I did a symmetry argument for the box one with the 4 particles with the same charge at the same distance. Then I did the symmetry argument. But the one before that,
Did I choose that one?
Yeah, it was fun. It wasn't hard. It was just a crap ton of work.
Yeah. Oh, and that's not really that's trivial to what we're going to be doing.
Oh my god, Padilla, you say
All right.
things like this.
But it gets way funner in a good way because we're really going to delve into the calculus today. So let's do part B and then move on. Part B. So what does the field do at part B? Well, we know that the bottom here is 26 centimeters and 26 centimeters. So let's erase all this stuff here. That's the nice part about having the iPad Pro. So if we did use the Pythagorean theorem there, we would find those are 40 centimeters, right? So let's draw the vectors due to both of those. So which way would the vector field due to charge 2 point?
No way.
What quadrant would it point to?
1.
Quadrant 1. So we have, that would be E, or what am I going to call this?
EB1 or EB2.
EB2. Which way would EB1 point?
Just reflected across the y-axis. Wait, no. Hold up.
Down towards. Yeah.
EB1. And here's the nice part about this.
Symmetry.
Symmetry argument. Symmetry argument is going to be very important in understanding and arguing right away that we don't have to do all the math. And we're going to do the math just right now, just to see it, not in its full force, but just to show that, hey, look, EB1 and EB2 actually cancel out. In which dimension?
The y's.
The y dimension. So if we look at EB1, we get EB2x. Then we get EB1x. Would you say both of those point in the same direction?
Yes.
Yes. Then you get EB2y. And then you get EB1y. Well, EB2y is going to be EB2, and we'll say this would be theta 2, and I'm going to say that would be theta 1. So this is going to be sine theta 2, and this is going to be negative EB1 sine theta 1. But we know that EB1 is equal to EB2, the magnitude, right? Because they're all equal to KQ over R squared. R's are equal. R1 is equal to 40 centimeters. R2 is equal to 40 centimeters. The magnitude of Q is exactly the same, 50 microcoulombs. So what's going to happen?
They're just going to cancel each other out.
Yes. So
And you know that theta 1 is equal to theta 2 as well.
theta 1 is also equal to theta 2. Therefore, in a situation like this, you don't have to write all this out. I'm just writing it out for just for teaching it. So I would want to see a statement, or I need to see a statement that says something about those components. So therefore, EB2y and EB1y cancel due to symmetry. So if you have a symmetry argument, you need to state that. You don't need to write all that out, but you can, just to see how it works out. Understand theta 1, theta 2, KQ, R squared, R's are the same, Q's the same, K is a constant. It all cancels out. So you need to make a symmetry argument. You can't just ignore it. And if I'm testing you, I would at least want to see EB2, EB1y cancel due to symmetry, or the y components of the E field cancel due to symmetry. All right, so let's go down here, part B. EB2, EB1, theta 1, theta 2. And we know that EB2x and EB1x are exactly the same, right? So in other words, if we're doing x and y components for both those E fields, we don't even look at the y side. Those cancel due to symmetry. So let's just look at the x side. And are those going to be the same as well?
Yes.
And they're not going to cancel out. They're just going to add on top of each other.
They're going to add on top of each other. So EB2x is EB2 cosine theta 1. EB1x is EB1 cosine theta 1. That would be 2. Theta 1 is equal to theta 2 due to symmetry. Therefore, the sum of the E field in the X direction is going to be EB2X plus EB1X. Now we need the magnitude. EB2 is equal to, what would that be? KQ over R squared, 8.99 times 10 to the 8th. I'm sorry, I think it's newtons meters squared over coulombs squared times 50 times 10 to the -6 coulombs over 0.40 meters squared.
2.81 times 10 to the 6th.
2.8 times 10 to the 6 Newton per Coulomb. Anybody else?
Yep, looks good.
So EB1X is equal to EB2X. Therefore, the sum of the X direction, I can just simply write 2 times EB, you can pick either one, it doesn't matter, 2X. So that's 2 times EB, 2 times cosine theta 2. So we have the magnitude, so now we need to find the actual angle, right?
It's just 30.
So what's the angle?
30.
Is it?
Yeah. Because you know that theta 1 is equal to theta 2, and you know theta 1 is 30 because of the two parallel lines cut by a transversal property.
So inverse tangent, 30 divided by...
Wait. You know what? I'm retiring. Goodbye, guys.
Enter, exit. Does anybody have a correct angle for me?
$49.
49 degrees, right?
Yep.
That would be theta 1. That would be theta 2. Tangent of theta 1 is equal to 30 centimeters over 26 centimeters. And if that's theta 1, that has to be theta 1. So inverse tangent, 30 over 26, I get 49 degrees. So I'm down here. Sum of the X component is 2 times 2.8 times 10 to the 6 Newton per Coulomb times cosine of 49 degrees. And the sum of the field, the total field, E net, is equal to all of the components in the X direction because everything cancels in the Y direction. And what do I get? Anybody have an answer for me?
3.7 times 10 to the 6th.
3 points. What do we get? Is it 3.6 or 3.7?
7.
7, it should round up.
Times 10 to the 6th Newton per Coulomb. All right. 2-minute bathroom break. I'll be right back.
I kept getting 0.86 degrees because I forgot I was in radians.
I kept thinking it was that good.
Okay. So whatever you're doing right now, stop doing it and really try to focus on what I'm about to lecture on. All right. So we've been doing point charges. We can do this all day, and it's really just kind of an exercise of chapter 3, or what you would call vector dynamics. You're describing a field, right? We're describing essentially a force field, which is the electric field. You put a particle in this field, what direction does it go? Now, we understand the gravitational field, right? You put a point mass, or you put a mass in the gravitational field near a huge gravitational field like the Earth's field, what happens? What direction does it go in?
Away. Towards.
It goes towards the center of the Earth, right?
50-50.
So that's all we're really dealing with mathematically, is just saying, what is the direction of the field? And if you get the direction of the field, you can predict the particle, which way it will go. Then you can use your force equation to predict, oh, it's going to have this acceleration. And if it has this acceleration, then you can further predict distances. So that being said, what about a charged ring? What about a charged length or a line? What's the electric field look like for charged objects now? So the whole thing is charged. The whole ring is charged. What does the electric field look like around something like that? And that's going to be the game we play now. We're going to pick specific points, and those points, only because we can't use calculus 3 yet, we have to be points of symmetry near these objects. So that being said, we're going to start off with a ring of charge. So say I take my ring here, and that's weird, kind of blanks out. And say I draw a line right through the center. What does the electric field do to the ring right here at this point? We're not talking like right over here, right over here. You would have to get a whole vector field. And that's what calculus 3 deals with, vector fields, like how all the vectors look around something that is charged. That's essentially what you want to get when you're actually coding something. Like, how do you produce a vector field? Question.
Are you drawing anything on the whiteboard, or
no?
You're not? Okay, cool. I heard you talking about like sphere. Okay, cool. Sounds good.
I was just hoping you were looking at me.
Okay.
Here, let's do this. Can you see me now?
Oh yeah. Much better.
So say we take this ring. Say we take this ring here and we make it positive. The whole thing has a positive electric charge. Along this line, there's a point right in front of it. What does the electric field do to that charged ring? And if I move really far away, how does that electric field influence that point really far away? So now we're going to be dealing with charged objects, not these point-like particles. The point-like particles you should be able to do all day long. Any kind of geometric configuration with point-like particles. And I'll probably have one problem on the test that does point-like particles, because those can be fun, but those really just reinforce your vector dynamics and your how to do vectors again. But this is the crux right here, is moving on to something more sophisticated like objects that are charged. And we're just going to do a few different types of objects and then look at all the different orientations of how to attack that. And it gets pretty sophisticated in terms of the way you approach those problems. So let's start out with the ring of charge. So let me go back to sharing the screen. All right, can everyone see that?
Mm-hmm.
Okay, so this is E field for continuous charge distributions. All right. So first of all, we need to get a little philosophical first.
Let's go.
So this is the argument. Whenever you try to understand anything and you're not understanding it, you try to break it into constituent parts. In other words, you try to understand the smaller systems that create the bigger systems to get an overall understanding of how the whole system works, right? That is my argument, Padil's argument, for infinitesimal pieces. So if I can break things up into these really small, tiny pieces and then add up, because I know I'm breaking them up into such a small piece that all those small pieces are exactly the same. So all I need to do is add up all those small pieces, and then I can get a picture of the whole. And that is the same exact concept mathematically that we do with making an infinitesimal piece of charge distribution on a piece of matter. So the first thing we're going to do is, let's make a ring of charge. So here's my ring. That's the side view, which in 3 dimensions, if we go from the middle, I'm going to pick a point right out here in space, and I'm going to call that point P. And so this is a symmetry argument again. So this is the ring sideways. This is the ring sideways. And of course, this ring has a radius A. All right. So this isn't a point charge anymore. This is a ring of charge.
Sounds ominous.
So if I have my basic equation, E is equal to KQ over R squared, I cannot describe the electric field at that point with that equation. But the equation gives me a mathematical starting point, which means I can make infinitesimally small pieces of the ring by making dE a differential. In other words, if I write dE, what do I want to break the ring up into? I want to break it up into a bunch of dQs. The distance is going to still be the same. K is a constant. So this dQ is just a differential part of the ring, right? This dQ causes this dE, this differential E field.
So even with an object that's completely charged, it doesn't have an an even charge like throughout. Because if you have a different,
we're saying that DE and DQ are a composition of a whole bunch of those. So I'm going to say, this is the question. Oh, wait, no. We have a little more to go first. So I'm going to break this ring up into a bunch of DQs, differential pieces of charge, which are infinitesimally small. That's the mathematical language for differentials. So relative, that's the physics interpretation. This ring also has a density to it, a charge density. So there's another thing that we need to learn. It's called linear charge density. And that is defined by lambda. Lambda is equal to the total charge of the ring divided by its length, which makes sense, right? How much charge do you have per unit length?
Length is in like the perimeter? Or
What? Or you could just do linear density. How much of something do you have per unit length? How much of something do you have per unit area? How much of something do you have per unit volume? It's always linear density, area density, and volume density. Those are what you'll see time and time again throughout any type of engineering program. So this is our linear charge density. We can rewrite it as Q is equal to lambda L. Lambda, our linear charge density, is going to be constant for now. Chapter 22 is going to deal with playing with that a little. So we can write this here. We can define DQ in a different way. So I'm going to make that a differential now. If I make DQ a differential, that means I have to write DL. So I'm breaking up DQ into lambda times DL. So there's a differential length involved. And that differential length is infinitesimally small. And this is where integration becomes very important. Because if you have a DL, guess what you can do with integration? What do? You sum up all the DLs. All right. So the game we're playing is trying to find the electric field due to these distribution of charges. The distribution of charge here is a ring of charge. That's going to be our first example, our first problem. Let's actually write out the example. Determine the E field at point P, a distance x away from the center of the ring. Let lambda be the charge per unit length, coulombs per meter. And that is called, the charge per unit length is called the linear charge density. All right. So this is why you're taking this class, to learn these new things. So this is something you're going to have to learn. This is a new way of attacking problems. This is the most rigorous way to actually do these problems. And if you continue in maybe electrical engineering, you will invoke three-dimensional calculus, spherical coordinates, cylindrical coordinates, and polar coordinates to solve these types of problems to get a true E field, vector field around a ring of charge. And, you know, nowadays they're asking you to actually simulate that. And you can use programs like Mathematica. And that is a program we will be using in our class to look at vector fields in 2 dimensions. All right, so we just want to know which direction the E field points at point P due to this ring of charge.
Wait, video.
Yeah,
Okay, I have a little bit of a conceptual question.
okay.
So the ring, are we doing all of this work because you're saying that there's like infinitely many points in the ring that have a charge, or the charge itself has like infinitely many little charges in it?
Yeah,
Or-
so this whole ring right here, this whole ring has a positive Q charge. All right?
Okay.
That whole ring has a positive Q charge. But in order to figure out what the E field is right here at point P, I'm going to break that ring into small little pieces of that whole Q. And what I'm going to do is say, I'm going to take a small little piece here and call that dq. And that's equal to lambda dl. And then what I'm going to do is I'm going to sum up all those little dq's around the ring in order to get the electric field at point P. So how do you do that?
You just integrate both sides, right?
So yeah, so let's look at some symmetry arguments before we start that. So if we look at, let's go green. So we know this is X distance away. Now the distance from that dq all the way to that point P is right there. And well, we can also pick dq at the bottom. All right. So the ring is uniform. It has uniform charge density. That's why I'm talking about linear charge density. That's important because you can build rings that have more charge on one side than the other based off of the metallurgy of the ring itself. But we're dealing with simple situations. Everything on the ring is totally uniform. The total charge is plus Q, and this is how I'm doing it. I'm breaking it up into these little dq's. Now, if you look at these dq's, here's point P. This is going to have a differential electric field at point P, pointing both ways, right? Because I know dE is k dq over r squared. Now, those dE's, due to the very top of the ring and the bottom of the ring, form like this cone. Can you guys see the cone?
Mm-hmm.
It's like a cone of dE's all the way around. We're just writing the limits of those dE's, which we can to make it easier and to do the problem. Well, that dE, the top dE and the bottom dE, guess what they have in common? You have a DEX. You have a DEY and a DEY. So what cancels?
The Y components.
The Y components cancel. So this ring if you were to bring a charge close to this ring along its line of symmetry down its middle, the E field due to this ring is only going to act in the X direction here. Does that make sense?
Just like that problem we did earlier.
Just like the problem we did earlier. But now this is an object.
Mm-hmm.
So this is our R. That would be our R. And that's totally symmetric. And all we have to do is look at one part of it. So this would be, call that theta. I'll call that theta. Everything is symmetric. So this would be theta, and that would be theta. All right. So let's attempt to do our first problem. Determine the E field at point P, a distance x away from the center of the ring. Let lambda be the charge per unit length. Okay, so you would want to draw a diagram out like this first to get everything in your head correct. So this would be a ring of charge. The other points around the ring, you would need three-dimensional calculus to figure out. So we're just picking the points that we can integrate basically in one dimension. Everything comes down to one-dimensional integration for this class. If we all had taken Calc 3 and you guys knew that, then we can use more sophisticated mathematics to analyze the electric vector field around a ring like this. Okay, so what is the E field there? So we know that the electric field in the Y dimension cancels due to symmetry at point P. That needs to be stated. So you always want to state that. And it's a simple statement, but you need to state it. Electric field in the Y cancels due to symmetry. And especially if you're writing code and you're trying to describe an electric property in some type of gaming app, you would need to put that in there. So really the electric field for this problem is only going to be in the X dimension. All right, so let's look at just simply DE. DE is always going to be K dq over R squared. That's what you're always going to start off with, DE. Now the next part is you want to do your notes. What I do is in the beginning, I always do the right triangle that I'm dealing with. This would be theta, that's my R, that's my A, and that's my X. That is that triangle right there. So I want to define the triangle I'm working with that describes that E field. So I'm going to write my functions down for that triangle. The first one would be R squared is equal to X squared plus A squared. And then I'm going to also write my trig functions. This is the bookkeeping that you need to do. Cosine theta is X over R. Sine theta is A over R. Tangent theta is equal to A over X. And this really helps. This really helps by doing this little bookkeeping. All right. Next part, I want to start analyzing the problem. So since we did our symmetry argument already, we're only going to look at the X component, DEX. Well, what's DEX equal to in terms of that right-hand triangle up there? that's going to be dE cosine theta, right? That dE is that dE right there. That's why we needed to define the dE. So let's go ahead and plug that in. dEx is equal to k dq over r squared cosine theta. All right. Now this is the really important part that you need to establish in your head. What variables are changing while you're integrating around the ring, and what variables are not changing? So you need to write a list. Change, not change. And let's go look at the picture. You look at this picture and you're integrating around the ring. As I integrate or add up dq around the ring, is the angle changing?
No.
Is x changing?
No.
Is the radius changing?
Yes.
No.
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 Oh, just in the ring, not the. Oh. Okay. Keep going.
So you're establishing constants here. You're establishing constants. So not changing. Well, what's not changing? X, theta, R, and A. The only thing that is changing is what we're going to define as L, the length of the ring. We're changing its position as we're moving around it, integrating. So let's go ahead and finish this off. dEx is equal to K. Now dQ, this is where we use our lambda dL to make it all come together. Lambda dL over r squared cosine theta. And I know k and lambda are constants, so I can keep them to the left. K and lambda are constants. What else is constant there?
The r squared and the cosine.
We could keep it all. So all we have is dl. And we can integrate both sides now. Well, dl is just a length, the differential length, right? Well, what is that differential length? That's just really just a very miniaturized differential arc length. So if you're integrating around a circle, what would be the limits of integration?
0 to 2 pi.
0
To pi.
2 pi a. Remember, that differential right there is a length, not a d theta. If it's an angle you're integrating around, that's fine. But what is 2 pi a?
Oh, the area.
Circumference, right?
It's the circumference.
Circumference.
Yeah, you're integrating around to get basically the circumference. So you're adding all those little pieces around, right? All those little differential lengths. And what should all those differential lengths equal to at the end of the day?
The circumference.
Driving me crazy. K lambda cosine theta over r squared times 2 pi a. Which would be, oh wait, let's do it a little more formally. What is the integral dl?
Just L.
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 with limits of integration from 0 to 2 pi a. K lambda cosine theta over r squared. Now you plug in your limits of integration, 2 pi a minus 0. We can forget about the 0.
Padilla,
Yeah.
if we were talking about symmetry earlier and how we're only analyzing one side, how come you aren't doubling the integral? Or are we doing that later? Or
We don't need to double it because we're integrating all the way around it. So we're adding everything around it together.
okay.
Because we were doing component vector analysis. Now how are we adding now? What are we doing? What does integration mean?
Like adding up all the little pieces?
We're adding up all the little pieces. So the integral takes care of all that.
And it's, oh, okay. Yep, I see. If you were to do it from 0 to pi, would that be double or no?
0 to pi, that would just be half.
But if
So
you double
you're talking
it,
about pi a.
okay.
No, Gabby, you could do 2 times the integral from 0 to pi, or you could just do the integral from 0 to 2 pi.
Okay, thank you, Josh. That's, yeah, okay.
All right, so we could put this as an answer, but we wanna, just like any type of formula, we wanna try to put it in its simplest form. And there's many, many interpretations of this, but here's how I want you to do it. Well, what is, first of all, I'm gonna isolate lambda, and I'm gonna write k r squared, and I have cosine theta times 2 pi a. Well, we know lambda is charge per unit length, right? We know lambda is the total charge per unit length. Well, what's the length of the circle?
The circumference.
2 pi
a. So I can put lambda, oh wait, no. I'm gonna actually I'm gonna write lambda as that, q over 2 pi a, k over r squared, cosine theta times 2 pi a. So 2 pi a cancels out just by plugging in what lambda is equal to.
What? So we're just left with the...
No, wait, we still have that
Okay.
cosine there,
Okay.
right? What's the cosine function equal to?
x over r.
X over r. So now I'm going to get q k over r squared. Now I'm going to write in what cosine is equal to, x over r. And what do I get? I get k qx over r cubed. And I go k qx, and now put in what r is equal to. Well, what's r equal to? X squared plus a squared. Or it's to the 3/2, right? X squared plus a squared to the 3/2.
Mm-hmm.
This would be your answer. KQX over x squared plus a squared to the 3/2. That would be the strength of the electric field at if you had a ring like that, you had a ring like this. Remember, we're not talking the ring is flat. We're saying from the center, it's along that line. There's a point right there. That would be the strength of the electric field there when you're X away. And this is just an approach. So you have to really practice these problems. You have to do a bunch of these problems to really get the feel for them. Now here's the cool thing. Well, what if X is much, much greater than A. What does that mean?
That A becomes inconsequential, and then you can cancel out the X on the top.
If X is much, much greater than A, then A approximately goes to 0, right? And e to the x is equal to kqx over x squared plus a squared to the 3/2. A goes to 0. What do you have? Kqx over x squared to the 3/2. 2's cancel out, and then I get kqx over x cubed, x cancel, and e to the x is kq over x squared.
Go back to the line.
Goes back to a point charge. So what does that mean? What is that telling you?
We did it right.
This telling you with this condition. What'd you say?
We did it right.
That means a ring of charge. If you're really far away from a ring of charge, what does it look like to you really far away?
A particle.
Point charge.
Point charge, right? And then as you get closer and closer and closer, what happens? You start to realize the effects of that piece of matter. It's like, you know, you see somebody real far away and you're like, oh, that's a human being. And then you get closer and closer and you're like, oh, that's a guy. And then you get really close and you're like, oh, damn, he's ugly. You know, it's like you get more effects. The closer you get to understanding, the more effects or more interpretation of what's actually going on.
So can't that be said about electrons and these tiny freaking particles that we're talking about? Because we're talking about point charges, but then that's going to translate into electrons and stuff.
Yeah. So you're jumping straight into quantum when you say that. We're just talking about the effects of the quantum world right now on a grand scale. So let's talk through the problem from the beginning again. Let's go to where we started. First of all, we're dealing with particles that have a continuous distribution of charge, right? So we're dealing with objects. The first object I picked was a ring of charge. The ring of charge has a positive Q to it, the whole ring. Now it's like the ring is sideways, and from its middle, we're propagating outward, and we're picking a point P, and we're saying, well, what is the E field along that point due to that ring of charge? Determine the E field at a point P, a distance x away from the center of the ring. Let lambda be the charge per unit length. Right away, you know you need to invoke your differential calculus, which means integration. So I'm going to break the ring into a bunch of DQs. I pick a point that is easy to analyze, which are the edges of the ring. So I write my DQ is equal to lambda DL. I propagate that DQ. I know that DQ has a DE at that point. That's why I write DE. That DE forms an angle, and I look at the components of that DE. There's a DEX and a DEY. So right away when I write that, I see that the DEYs cancel due to symmetry. It forms like this little cone of DEs all the way around it. And everything in the Y direction would cancel due to symmetry, because if we did DQ at the bottom of the ring, you could clearly make that argument. That's what gives us the ability to state EY cancels due to symmetry at point P. if that point was slightly above the x-axis, that would be a whole other problem. We're just looking at one point and saying, what is the E field at that one point? So now we go, okay, so DEY's cancel. That means the only component that we're dealing with here is DEX. That's what we need to analyze. You could go straight here if you wanted to. DEX is equal to DE cosine theta. Well, what is DE? Well, we know that DE is KdQ over R squared. Doing these problems, this kind of method is always going to be the same in the beginning. Very similar, where you're taking DE and you're plugging it into the component that actually propagates the E field, which is DEX in our case.
So DE will always equal DE cosine of theta?
DE will always equal to KdQ over R squared.
Wait,
This
would
will always be true, Chavez. DE is equal to KdQ over R squared.
would the formulas for DEX and DEY also be the same ones? Like, you know what I'm saying?
In this situation, they would.
But in
Right.
other situations, you would have to make it different.
Yeah, would there, so what if we had a ring of charge and I said, right here in the circle, what's the electric field right in the middle of the ring of charge?
Gabby, we can't hear you.
Was Gabby talking?
No, I don't mind. It sounds, no, I was dumb. I shouldn't, it was, never mind.
Say it. There are no dumb answers. Look at me.
Here's a Q of charge. What is the electric field right smack in the middle? Not moving away from the center, but right in the center of a ring. What would the electric field be?
Nothing, right?
Why?
I don't know. I remember when we talked about.
Okay, hold on, Padil. Can
You're
you
pulled
repeat
equally
the
in all
question?
directions. It's equal pull in all directions. Or push, whatever. You're in balance. That makes a lot of sense, Gabby.
Here's a DQ here, right? Well, if we
Right.
propagate that, that's going to be DE here, right? That's going to have components. DEY.
Right.
Do a DQ here.
Yeah, so it's literally just going to be a tiny circle with a crap ton of arrows all pointing outwards.
Exactly. And what do all those arrows do with each other?
Cancel out.
Cancel out.
Cancel out. So what's the E field in the middle of the charged ring?
0.
My hero.
Gabby, good job.
In middle. So if you have a charged object, right? You have a charged object, the electric field in the middle is 0. That is the beginning of understanding what we call a Faraday cage. Because whenever you have electronics, you want to protect those electronics, right? So now you can put the electronics in an electric cage where everything inside cancels out, so nothing will affect the electronics inside the center. It's a weak argument for a Faraday cage, but it's still a valid one.
And the same thing would happen if the charges were reversed, right?
And the same thing would happen. So it doesn't matter. That's what makes it so nice, is that if it's positive Q or negative Q, what's the total charge in the middle? I mean,
Still
what's the
0.
total E field in the middle? It's still going to be 0. All right. So in a problem like this for a ring, we're just choosing a ring. You're gonna actually do some problems in your homework, the next homework that I'm gonna post today, moving that point. Well, that point I wanted to show mathematically. Show me mathematically it's 0 in the middle. That's what you're gonna have. That's one of the problems. So we establish our DE is KdQ over R squared. We can plug that. We understand that DEX is the only variable that we need to deal with in terms of the E field propagating in the X direction, then we do our bookkeeping. We create the triangle that we're working with. Create the triangle that we're working with and write out all our bookkeeping notes. And then we say, when we integrate around it, what variables are changing, what variables are not changing. So we establish that.
Of L is the only variable that's changing.
L, it's only changing its position around because we're integrating all the way around.
And is that always or?
That'll be always, yeah.
Okay.
So K lambda DL cosine theta, now it's just a matter of attacking the integral. Well, everything is constant. This changing, not changing is important to do because it lets you, it tells you what you need to integrate and what you don't need to integrate. If X, theta, R, and A are not changing, that means they're constant. So you do not need to integrate over them because they're a constant. However, for the circle, you need to integrate around the circle. So you do that, you integrate 2 pi a. And the rest of this is just algebra and representing the problem. It's a matter of practice. The idea is whenever you have a formula like this, you want to always have the Q in the formula. And then you want to break down the R. You want to put the R in its full form. And you never want to leave it as cosine theta, like up here in the problem. You always want to put what cosine theta is. So you're reducing the problem to its, kind of like it's, what do they call that in algebra?
Opponent?
Like it's least,
Least common denominator?
no, not least common denominator.
Least common factor?
No.
Like when you reduce something to the most it can be reduced.
Yeah, you want to reduce it to the most it can be reduced. There's the long form of saying it.
Yeah, that's. I know what you mean. I can't think of the
Yeah.
word.
Yeah, so you want
Oh,
to
least common multiple.
Simplify?
LCM.
Right?
I remember that.
Simplify something.
just simplify the equation. There you go. Simplify the equation, and as you can see, we simplified it to a point where we made just one assumption: x is much greater than a. What happens? Oh, boom, we got kq over x squared, which means if we're really far away, that ring charge doesn't look like a ring charge to us. It just looks like a point charge. But as you get closer and closer, oh, you start seeing the effects of the ring. And that changes into that. So it's a distance thing. Yoel.
So is our answer always going to be in the form of the equation, or do we have to plug in numbers in like a different problem?
Oh, right now it's all equations.
Gotcha.
We're just going to do equations for now. I will you will start plugging in numbers though. I would have to give you a q, a distance, and a radius here, right? In order to actually get an answer for this.
Yeah.
Yeah. But what I'm teaching you now is how to attack these using rigorous mathematics. And this is all one dimension. We're just breaking this into one dimension. And this is just in the x dimension. All right. 9:53.
7 more minutes.
I don't think we have time to do all I want to do.
Let's talk about life then, Padil.
Oh, it's all right, man.
What? Bye. Love you. Oh.
The magnitude of an E field at point P, a distance x away, from the midpoint O of a very long line wire of uniformly positive charge. X is much smaller than the length of the wire. Okay, determine the magnitude of the electric field at point P, a distance x away from the midpoint O of a very long wire of uniformly distributed charge, distributed positive charge. X is much smaller than the length of the wire. All right. I want you guys all to, guys and girls, to learn this method. That's a wire. There's my point P. Positive Y, negative Y. There's my 0 point. Positive infinity, negative infinity. So we just have a wire. And it has plus Q on it. And I'm asking you, what is the electric field at point P there due to this infinite wire? What is the equation that governs that? So an infinite wire, basically, or we could say a very long wire of uniformly distributed positive charge is much smaller than the length of the wire. All right. Guide me. What's the first thing you would do? Anyone?
Bookkeeping.
Okay.
Draw stuff.
So bookkeeping, we have to draw stuff. So what do we want to do to the wire, first of all? What do we want to break it up into?
Smaller and smaller lengths.
A triangle.
So we want to break it up into our DQs. Now that DQ right there is going to have an electric field at point P, right?
Mm-hmm.
But that's a differential electric field. So we make a symmetry argument right away.
Yeah.
Yes. What happens?
DEY
The
cancels
Y's
out.
cancels out.
DEYs cancel due to symmetry. And this will change because I will have problems given to you where the bottom half is going to be shorter than the top half. And I'll give you lengths, which means would DEYs cancel then?
No.
They would not. So in this problem, DEX, DEY, DEY. So due to this infinitely long wire, what is the only direction the E field will point due to the wire?
EX.
X direction. So now I can say DEYs cancel to DE due to symmetry. So DEX is equal to what? Well, if this is theta, I said this is X. Remember, the length from DQ to point P is always defined as what?
R.
R. Now we have a distance from O up to DQ. We're going to define that as O. Why?
Not A?
Why A? It's not A is a radius. We're on the Y dimension.
Okay.
We're dealing with just a wire, not a ring. So if this is theta, that would be theta. We can make, you know, we could keep going there. Theta here, theta here. So DEX is DE cosine theta. We know what's DE equal to in general.
K DQ over R squared.
DQ over R squared. So DEX is equal to K DQ over R squared cosine theta. And what is DQ equal
Lambda.
to in general?
Lambda times DL.
DL. DEX is equal to K lambda DL over R squared cosine theta. But what dimension is L in?
The Y?
Yes. We can write DQ as lambda dy now, because now we know it's in that one dimension. Before in the ring problem, that DL was just this little tiny miniature arc length. Now this is in one dimension. So we can say DL here is dy. All right. We got to end there because I need to get to the lab, and I think so do other people. We will continue this problem on Thursday. This problem is straight out of your book. If you want to try to attempt it, go for it. This is a difficult problem. And that's why I like going slowly through it. But we will continue this on Thursday for sure. Remember, bring your what?
First day handouts.
First day handouts to lab.
Also, Padilla, do you have any extra first day handouts?
You left your first day handouts there. We have what you left there.
We didn't take them home?
You didn't. Other people did.
Oh, okay. All right. Epic. All right.
All right.